So I'd like to talk today about complete pick spaces. And after the introduction, the material at the end is joint work with Alexandru Alaman, Michael Hartz, and Stefan Richter. So let me start the story. And very appropriately, the story begins right here in Lancaster with Peter Quiggin, who was a PhD student under Nicholas Young. And in 1993, he published a paper in Integral Equation and Operator Theory with the title, "For which reproducing kernel Hilbert spaces is Pick's theorem true?" So what does this mean? Well, every good story has a backstory. So let's first start with Pick's theorem. So your Pick, it always used to be quoted as 1916. He published this but it was during the First World War, and now there's been some historical changes, and now gets auto-corrected in 1915. So I'm not sure when the paper actually appeared. Anyway, Pick considered the problem of if you start with n points in the unit disk and n complex numbers, when can you find a map that sends the unit disk to the right half plane that maps your points lambda j to the appropriate target? So for the purpose of this talk, we're going to do a Cayley transformation and instead of mapping to the right half plane, mapping back into the unit disk. So the question then becomes, given points lambda 1 through lambda n and w1 through wn, when can you find a function that maps the disk to itself? That's the same as saying it's in the unit ball of h infinity, which is holomorphic, and it sends lambda j to wj for every j. And Pick gave a complete answer, namely you look at the n by n matrix you form, the so-called Pick matrix, 1 minus wi wj bar divided by 1 minus lambda I lambda j bar, and that needs to be a positive semi-definite matrix. All its eigenvalues have to be greater than or equal to 0. Now, that's Pick's theorem. It doesn't say anything about reproducing kernel Hilbert spaces. So to make sense of Quiggin's question, we need a little bit more backstory. And this is an observation of Donald Saracen in 1967, that the requirement that phi be in the unit ball of h infinity and phi map lambda j to wj can be interpreted in terms of the Hardy space H2. So the Hardy space H2 of functions with holomorphic functions with square summable Taylor coefficients on the unit disk, the multiplier algebra is isometrically isomorphic to h infinity. So the condition that phi be in the ball of h infinity is exactly the same as the condition that, maybe it's better if I highlight here, is exactly the same as the condition that the multiplier norm from h2 to h2 is less than or equal to 1. And then the interpolation condition, that phi of lambda j is equal to wj, that can also be interpreted if you look at the multiplier operator. More particularly, if you look at the adjoint of the multiplication operator, m phi star, it's easy to show that for any multiplication operator, the adjoint satisfies m phi star applied to so I'm using s sub lambda to denote the Sega kernel. S sub lambda of z is 1 over 1 minus lambda bar z. That's the reproducing kernel at lambda. And it's an easy calculation that for any multiplier, the Sega kernel is always an eigenvector, and the eigenvalue is phi of lambda bar. So the condition that phi map lambda j to wj is exactly the same as saying the adjoint m sub phi star sends the Sega kernel at lambda j to wj bar times the same kernel. So what Pick is looking for can be expressed in terms of H2. So you want to find a function phi so that its multiplier norm is less or equal to 1, and the adjoint of multiplication by phi has certain eigenvalues at the kernel functions s lambda j. So in particular, if multiplication has norm less than or equal to 1, that's exactly the same as saying that on all of H2, the operator 1 minus m phi star is positive semi-definite. So if it's positive semi-definite on all of H2, in particular, it has to be positive semi-definite when you cut it down to a subspace. So if we choose the subspace spanned by the Sega kernels at the points lambda j, that's an n-dimensional subspace, and 1 minus m phi star has to be positive semi-definite on that space. But the advantage of working on that space is that you can calculate what this n by n matrix is very easily, because m phi star has s lambda j as an eigenvalue with eigenvalue wj bar. This will pull out the wj bar. The m phi I pull over to the other side. Maybe this would have been better with let's make it a little thinner. To the other side, and I get a phi of lambda I, which is wi. So, this expression here is equal to this expression here, just by knowing what phi does on the points lambda 1 through lambda n. And it's equal to the pick matrix 1 minus wi wj bar divided by the Sega kernel 1 minus lambda I lambda j bar. So the advantage of Saracen's formulation is that the necessity of Pick's condition comes essentially for free once you express it in the language of H2 as a reproducing kernel Hilbert space and H infinity is multiplier algebra. The content of the theorem now is proving that this necessary condition is also sufficient, namely that if you just know the values on lambda 1 through lambda n, and you know that on the n-dimensional space spanned by the Sega kernels, you have an operator that looks like the adjoint of multiplication by phi star, which is a contraction on that n-dimensional space. You can extend it to all of H2 and keep it as a contraction. So that now allows us, since we have a reproducing kernel interpretation of Pick's theorem, to make sense of Peter's original question. So now we can express it formally. So you suppose that HK is a reproducing kernel Hilbert space on some set X. And you're given n points, lambda 1 through lambda n in X, and then you're given n complex numbers. So I think of the lambdas as the nodes and the w's as the targets. So I'm given n nodes and n targets, w1 through wn. And the question is, can I find a multiplier of norm less than or equal to 1? So can I find a function phi in the closed unit ball of the multiplier algebra that interpolates? It maps each node to each target. It maps each lambda j to wj. And from the same argument we gave on the previous slide, the necessity part didn't use anything special about H2. That just followed from simple properties of reproducing kernel Hilbert spaces. So we always get that if you want to do this, a necessary condition is that 1 minus wi wj bar times the Gramian k lambda j inner product k lambda I, that always needs to be positive semi-definite. And then the question is, when is this necessary condition also sufficient? So that was Quiggin's question. And it wasn't entirely out of the blue. there were spaces other than the Hardy space for which the answer was known to be true. There were two known examples at the time, both due to Jin Agler. One is that the theorem is true in the Dirichlet space, the holomorphic functions on the unit disk whose derivative is square integrable with respect to area. And the second example is kind of a weird one because there's no analyticity involved. You just take the Sobolev space on the unit interval, W21 or W12, depending on your conventions. Since we work in holomorphic spaces generally, we don't like using H for Sobolev, so we use W. Don't know why nobody ever uses S. So the Sobolev space we're interested in is the functions in L2 whose derivative is also in L2. And this turns out to be a perfectly nice reproducing kernel Hilbert space on the unit interval. You can work out explicitly what the kernel function is. And it has the pick property. Whenever condition P is satisfied, you can always extend phi to a multiplier on the whole space with norm less than or equal to 1. And so Quiggin's question asks, can you come up with a characterization of all these spaces for which this holds? So, of course, we'd like to know the answer to Quiggin's question. And unfortunately, there's still no good characterization of spaces for which this pick condition is always sufficient. So that's the bad news. But there's good news. Since we're operator theorists, we know that it's often the case that if you ask for something to be true, not just at the scalar level, but also at the matrix level, then suddenly it becomes much easier to study. That saying a property is true at all matrix levels often turns out to require some very strong structure, which you can deduce. So what would the matrix valued version of Quiggin's question be? Let's call it the complete question. So as before, we assume that we have a reproducing kernel Hilbert space, H, and kernel K, on some set X. But now, instead of scalar valued functions, we consider vector valued functions. So let's fix D and think of functions that map X into CD, which the easiest way to think of it is just a D-tuple F1 through Fd of scalar valued functions. But now, for the vector valued functions, the multipliers are going to be D by D matrices of functions. A D by D matrix of functions on X will send a D vector of functions on X to another D vector of functions on X. So now in this vector case, Quiggin's question would become if you fix some D, and then you choose n points lambda 1 through lambda n in X, and you choose n D by D matrices, W1 through Wn. When can I find a function that's a multiplier of the direct sum of H with itself D times, and in the closed unit ball of that, have norm less than or equal to 1 as a multiplier? If the tensor notation looks a little scary, just think of that as the direct sum of H with itself. And the interpolation condition is that at each point lambda j, the function has to equal the matrix Wj. And then exactly the same argument as before, just done with matrices instead of with scalars, tells you that if you can find such a phi, then 1 minus multiplication by phi times multiplication by phi star has to be positive semi-definite on the entire space. And then in particular, if you cut it down to the span of the kernel functions, you get condition P here, that 1 minus wi wj star, that's now a d by d matrix, and you multiply it by the inner product of k lambda j with k lambda I. So you'll have this will be a large matrix that's size dn by dn. So this is dn by dn size matrix. That has to be positive semi-definite. And then that would be the pick condition. It's true in every reproducing kernel Hilbert space. And then Quiggins' question is, what properties of the reproducing kernel Hilbert space tell you that this condition is always sufficient? And we'll say that the reproducing kernel Hilbert space is a complete pick space if this necessary condition is always sufficient for every value of D. Now, the good thing about the complete question is that we have a complete answer. Quiggin gave a sufficient condition for a space to have the complete pick property. And around the same time, Scott McCullough was also thinking about the problem, and he proved the condition was also necessary. So we get the McCullough-Quiggin theorem, which says that if you have a reproducing kernel Hilbert space, H with kernel K, and we just make a little trivial technical assumption that it's irreducible. That just means that you can't split it into two pieces, that the multiplier algebra doesn't contain any non-trivial characteristic functions. Then a necessary and sufficient condition for the Hilbert space to be a complete pick space is that the reciprocal of the kernel, 1 over k, has exactly one positive square. What that means is that for any choice of points lambda 1 through lambda n, any n, I look at the matrix whose ijth entry is the reciprocal 1 over the kernel at lambda I, lambda j, that this n by n self-adjoint matrix has exactly one positive eigenvalue. So this is a very nice, very concrete condition. In fact, you can make it even more concrete with a fairly harmless normalization. So if you assume that there's some special point lambda naught, so if you're thinking of a space of analytic functions on the disk, think of lambda naught as being the origin, and then in most spaces you might consider the reproducing kernel at the origin is just the constant function 1. And indeed, you can always achieve this normalization, so it's a harmless normalization. The advantage of this, though, is if I take this matrix and I include the point lambda 0 as the first point, then the entire first row and first column are 1s. So if I take the Schur complement with respect to the 1, 1 entry, I get that, well, clearly the 1, 1 entry is positive. For all the other eigenvalues to be negative, the condition becomes that the matrix whose entries are 1 minus 1 over k, where 1 over k means the reciprocal of k, the pointwise inverse, that this be positive semi-definite. And this is a very easy condition to check whenever you have the kernel in a concrete form. For example, if you take the Hardy space, then the kernel is 1 over 1 minus w bar z. So 1 minus 1 over the kernel is w bar z, and that's manifestly positive semi-definite. So if I take any, so saying this is positive semi-definite says that for any choice of lambda i's, if I look at this, if I look at the sum ai aj bar times lambda I, lambda j bar, that's always going to be positive semi-definite. And that's obvious because it's just the sum ai lambda I modulus of that squared. When we look at the Bergman space, the Bergman kernel is 1 over 1 minus w bar z quantity squared. So if I take 1 minus 1 over the kernel, I get 2 W bar Z, but I have a minus sign here. The squared term comes with a minus sign. And because of that, that means that the kernel, this on any finite dimensional space will be rank 2. It'll have one positive eigenvalue and one negative eigenvalue. So it fails the McCulloch-Quick condition. And so the Bergman space does not have the complete pick property. A third example is the Drury-Arvison space. So the easiest way to define that is just to tell you what the kernel is. Namely, you fix some positive integer d, and then it's a reproducing kernel Hilbert space on the unit ball in CD. And the kernel is 1 over 1 minus the inner product of W with Z. So since W and Z are both in the unit ball, the inner product of W with Z is going to be less, has absolute value less than 1. And this gives us a kernel. And I apply the McCulloch-Quick theorem. I ask for this condition here. 1 minus 1 over K is just the inner product of W with Z. And again, that's manifestly greater than or equal to 0. So the Drury-Arvison space for every D has the complete pick property. So we have a very satisfactory answer to Quiggins' question in the complete case, that a normalized, irreducible, and as I say, don't worry about either of those words, they're very trivial to achieve. Reproducing kernel Hilbert space has the complete pick property if and only if 1 minus 1 over K is positive semi-definite. And you can go a little further with this observation. Since it's positive semi-definite, you can then use the Kolmogorov factorization to say that anything is positive semi-definite, you can realize is the inner product in some Hilbert space L of some L-valued function with itself. So this is the Kolmogorov decomposition of any positive semi-definite function. So you do a little algebra there, and you get that the kernel is 1 over 1 minus the inner product of B with itself, where B is some map from your set X on which the reproducing kernel Hilbert space lives into a Hilbert space L, and the dimension of L can be anything between 1 and infinity inclusive. So you conclude that every complete pick space is complete pick if and only if you can find this embedding B that sends X into the ball of a Hilbert space so that your Hilbert space H is the restriction of the Drury-Arvison space to the range of B. Now you can always embed in larger and larger D. So the largest one is if you take D to be infinity. So if I take the Drury-Arvison space on the unit ball of little l2, H to infinity, that is in some sense a universal complete pick space. A Hilbert space H has the complete pick property if and only if you can embed it in this way in H to infinity. So now that we have this nice characterization, do we have more examples? Well, we've already seen the Hardy space and the Dirichlet space and the Drury-Arvison space. There's an encompassing version of this of various Besov spaces. So you look at holomorphic functions on the unit ball in CD, and you take their radial derivative. So the radial derivative sometimes called the number operator because, let me just write it out in 2 dimensions because it's easier. I take z1 to the m, z2 to the n, that maps to m plus n times z1 to the m, z2 to the n. And the same in more variables, just write it this way for simplicity. So in this form, it's easy to see what powers of the radial derivative are, even fractional powers, the s r sub s. We'll just take that to the power of s. So I can do this for any fractional power. And then I can define a Besov space by, I take s radial derivatives, then I take the modulus of that squared, and then I multiply by some radially decreasing weight. The simplest example is I take 1 minus modulus of z to some power alpha, and then I integrate that with respect to volume measure. I want that to be finite. And then in 2019, Alman, Hartz, Richter, and I showed that you will have the complete pick property provided you take enough derivatives. And the condition is the number of derivatives you take has to be greater than or equal to alpha plus d over 2. So you can check that the first 3 examples are all special cases of this. The Hardy space, you take 0 derivatives. D is 1, but alpha is minus 1. In some sense, you can think of the Hardy space on the disk as if you take the limit right, it corresponds to integrating against 1 minus z modulus z to the minus 1 over the unit disk. The Dirichlet space, you take 1 derivative, so s is 1, alpha is 0, and d is 1. The Drury-Arvidsson space can also be realized as one of these Besov spaces. So one tends to think of spaces where the norm is just defined by an L2 norm as simpler to deal with. If you want the pick property, for some reason, you seem to need to involve derivatives, which makes the norm less localized in some way. Okay, so the title of the talk was, what are complete pick spaces and what are they good for? So I've told you what they are. The next question is, what are they good for? Well, the theme is that many properties of the Hardy space that seem to be function theoretic actually can be thought of as operator theoretic and carry over to all complete pick spaces. So for the rest of the talk, I want to illustrate this. Well, I'll call the first example example 0 because it's a little bit of a cheat since it almost follows from the definition of what it means to be a complete pick space. But everything that's known about Neven-Linna pick interpolation on the disk generalizes to complete pick spaces. So this includes the network realization formula, what I like to think of as the ABCD of the theory, the Neven-Linna parameterization of the solution. Sorry, I misspelled parameterization there. And Leach's theorem, which used to be called the Toeplitz-Corona theorem until somebody discovered that Leach had proved this in the 60s and nobody would publish it because it wasn't sufficiently useful. But as I say, these in some sense, this shouldn't really be considered an example because the complete pick property is defined in terms of behaving nicely with respect to interpolation problems. So let me give some other examples. First one I'll give is interpolating sequences. So first, let me give a definition. We say that the sequence lambda n is an interpolating sequence for the multiplier algebra of a Hilbert space H if for any sequence Wn in little l infinity, any bounded sequence, I can always find a multiplier on H which at the nth point takes the value Wn. So in some sense, the lambdas are sufficiently spaced out that you can choose the values of the multiplier arbitrarily at each one. And Carlson characterized interpolating sequences for H infinity in 1958. So in this theorem, I'm going to use K for the Sega kernel for H2. Earlier, I was calling it S, but now I'm going to call it K. So there are several ways of stating Carlson's theorem, but this is one of them. The sequence lambda n of points in the unit disk is interpolating if and only if it satisfies two conditions. The first one is called weak separation. And that says for every pair of points, lambda m and lambda n, if I take the inner product of the normalized Sega kernels at lambda m and lambda n, the absolute value of that is less than 1 minus epsilon. So there's some fixed epsilon, not depending on m and n. So I guess I should have said there exists epsilon greater than 0, such that this holds for every m and n. That's called weak separation because you get it just by checking every pair. You don't compare one point to all the rest at once. So pairwise, they're separated. That's weakly separated. And then the second condition is what's now called the Carlson measure condition, which says if I take any function in H2 and I integrate it against an atomic measure whose mass at the point lambda n is 1 over the norm of the Sega kernel squared there, if I take the integral of f squared, so since it's an atomic measure, that just becomes the sum on the left-hand side here, the sum of the function at lambda n squared divided by the norm of the Sega kernel at lambda n squared, that this is always less than or equal to some constant times the norm of f on H2. So for complete Pick spaces, Alman, Hartz, Richter, and I showed that exactly the same theorem is true. If you have any complete Pick space, HK, then a sequence lambda n is interpolating if and only if it's weakly separated and it satisfies the Carlson measure condition. Okay, so interpolating sequences behave, and as I say, this is slightly strange in that the proof of Carlson's theorem seems to require quite a lot of function theory, and yet somehow it still magically carries through to all these complete Pick spaces. A second example is if you take the weak product of a Hilbert space with itself. So this is supposed to be an analog of H1. You can do it for any reproducing kernel Hilbert space H. The weak product of H with itself is I take all pairwise products Fn, Gn, where Fn and Gn are both in the Hilbert space. I sum them up, and if I can do this with a sum such that the sum of a norm of Fn times the norm of Gn is finite, then that's a function in the weak product. And the infimum of these norms over all such representations will be the norm in the weak product. So this was introduced by Koifman, Rockberg, and Weiss in 1976, and it's a way of studying H1 for the classical Hardy space on balls and polydisks. So you can do this in any reproducing kernel space, but in complete Pick spaces, this weak product is particularly nice. So let's suppose we have a complete Pick space, and we're also going to suppose it has the column row property. I'll explain to you on the next slide what the column row property is, but let's assume it has this extra mysterious property. Well, then three things are true which are analogous to theorems about H1 on the disk. The first one is that there's a natural bijection between the multiplier invariant subspaces of the Hilbert space and the multiplier invariant subspaces of the weak product, just like the invariant subspaces of H1 are still just given by an inner function times H1. Berling's theorem is the same as in H2. The second result is that the weak product, a priori, you have to take infinite sums. But in this case, you don't. Everything in the weak product is just a single product, f times g, of functions in the space. It's not obvious at all that that's even going to be closed under addition. That's not even obviously a subspace. But Michael Jury and Rob Martin proved this in 2019. And what's perhaps even more surprising is their proof proves it first in the non-commutative case and then deduces the commutative theorem from the non-commutative theorem. And as far as I know, there is no proof of this that doesn't go through the non-commutative route. So this is an example of how non-commutative analysis can sometimes help you prove commutative theorems, even if you don't care about non-commutative case in the first place. And then the third property is that the weak product has the same multiplier algebra as the original Hilbert space. And again, you're supposed to think here the multiplier algebra of H1 is H infinity. That was proved by Raphael Cloatre and Michael Hartz in 2020. Okay, so this all depended on this mysterious column row property. So what's the column row property? So we'll say a Hilbert space has the column row property if whenever I have a column that's bounded, so a column of functions naturally maps H to H tensor little L2. So each phi here is a multiplier. So a column of multipliers will send a single function f in H to a column of functions. That'll be in H tensor little L2. And the column row property says that whenever that column is bounded, the corresponding row is bounded. So a row of multipliers will naturally map a column of functions in H to a single function in H. So the column row property, notice I haven't taken an adjoint. Adjoints obviously are going to preserve norms, but I've taken a transpose. And transposes can be tricky. So any Hilbert space whose norm is given by an L2 norm, like the Hardy space or the Bergman space, then the column norm and the row norm are always going to be the same. It's fairly easy to check that it's just the pointwise suit of the little L2 norm of the column over the set X. So you get the column row property automatically in Hilbert spaces that have an L2 norm. But the ones we're interested in have derivatives. So this property was first observed by Tavan Trent in 2004, and he proved that the Dirichlet space has the column row property. And he proved it with a constant of square root of 18. Then we showed that Besov spaces, including all the Drury-Arvidsson spaces for finite D, also have the column row property, but with some constant that blew up with D. Then last year, Michael Hartz proved what I consider the most amazing theorem in this subject since the McCulloch-Quiggin theorem, that every complete Pick space has the column row property with constant 1. So it has it isometrically. So this is really an amazing result. And as a corollary, I can take my previous theorem about the weak product and then say it now applies to every complete pick space, because the hypothesis that you have the column row property turns out to be redundant thanks to Hartz's theorem. So the weak product is always just the product. It's just everything that can be written as a product of two functions of the Hilbert space. Their multiplier algebras are the same, and the multiplier invariant subspaces are the same. Okay, so now we need some Fourier analysis. If you're bored, you can choose your favorite number and work out its Fourier transform. Moving on. Suppose we have what we consider an analog for H1, namely the weak product. So we'd like to get something that corresponds to HP. So we're going to define curly HP by interpolation in the Calderon sense, complex interpolation between two Banach spaces. So at one end of the scale, I take the weak product of H with itself. And at the other end of the scale, I take its anti-dual, the conjugate linear functions. So the reason you have to deal with the anti-dual is because of this unfortunate fact that Hilbert spaces aren't actually self-dual because of the complex conjugate linear product. A Hilbert space is naturally isomorphic to its anti-dual. And likewise, if you think the dual of HP is not isomorphic to HQ, but to the complex conjugates of HQ. So if you work with the anti-dual on a space of analytic functions, everything will be analytic. So Calderon's interpolation method says if I take any two Banach spaces with a dense intersection, I have a scale joining one to the other. And this is an analog of the LP scale. That was where it first arose. So on the unit disk, this would correspond to H1, and this would correspond to BMOA, the analytic functions of bounded mean oscillation, which is slightly bigger than H infinity and smaller than every other HP space. And if you do Calderon's complex interpolation between H1 and BMOA, you indeed get the HP spaces. So we were able to show some properties of that. So you start with the complete pick space, and you define curly HP by this interpolation. You automatically get, by the way, curly H. So the reason P and theta have this form is that the midpoint, theta is a half, corresponds to P equals 2, and you always get the midpoint of this, just gives you your Hilbert space back again. But for P between 1 and infinity, well, we get a couple of extra properties. We get that the anti-dual of HP is isomorphic to the space HP prime, where as usual, 1 over P plus 1 over P prime is 1. We get that the evaluation functional at a point W, we'll call that delta sub W, that is a linear functional on HP. So I guess, sorry, this should be HP star, not HP dagger. The norm of that linear functional is comparable to the kernel at WW to the power 1 over P. Again, this is true in the Hardy space. And we were also able to show that the space H and its weak product have the same interpolating sequences. So a little history there. In 1962, Shapiro and Shields gave a new proof of Carlson's theorem, in the course of which they proved that the Hardy spaces H1, H2, and H infinity all have the same interpolating sequences. And then Marshall and Sundberg, in a very influential paper from 1994, which is actually where I first learned about the pick property. This paper never got published. And the preprint used to be on Don Marshall's website and has disappeared, but it's a great paper. They prove, they're trying to characterize, well, they do characterize the interpolating sequences for the Dirichlet space, but in the process, they show that for any Hilbert space that has the pick property, the Hilbert space and its multiplier algebra always have the same interpolating sequences. So this extends that now from H to its weak product. Whether this is true for the HP scale, we don't know. Let me give one last example. I'm running out of time, so I'll go a little quickly here. Inner-outer factoring. This is a key to understanding function theory in the Hardy space. So we're going to say a function is sub-inner. If it's a multiplier, it has norm 1, and it's isometric on at least one function. There's some non-zero function h such that phi multiplied by h, the norm of that is exactly equal to the norm of h. Notice that any inner function in H2 is isometric, so this holds for all h. And then we'll say the function is free outer if at some point z0, the real part of h at z0 is bigger than or equal to the real part of g of z0, where g ranges over all functions with the property that phi g inner product g is equal to phi h inner product h. So let's think again in H2 what that would say. If I have any inner factor u, if I have phi u h u h, if I'm in H2 and u is inner, then in the integral that just becomes the integral of the modulus of u squared, which is 1, so that cancels out. So in H2, this set here is just the set of things that has the same outer factor as h. And so this will be a definition of outer in the Hardy space. And let me skip the next bit. So in 2019, Jury and Martin showed that in every complete pick space, you can always factor a function as a sub-inner times a cyclic function. You can show that every free outer function is cyclic, but not conversely. If you replace cyclic by free outer, you get a unique factorization. Every function can be uniquely factored as a sub-inner times a free outer. And in the free product, you can factor every function as a sub-inner times the square of a free outer. So a big question here that we don't know the answer to is whether everything in HP looks like phi times h to the p, where phi is sub-inner and h is some free outer. That would be a great characterization of HP, but we have no idea how to prove that. And finally, let me close with the only example I know of a property that the Hardy space has that doesn't generalize to complete pick spaces, and that's the Corona theorem. The Corona theorem fails spectacularly in complete pick spaces. Thanks to an example due to Hector Salas in 1981, he proved that there exists a complete pick space of holomorphic functions on the unit disk that are continuous up to the boundary. And they really do live just on the unit disk, in the sense that if I take any partially multiplicative functional, something that's multiplicative whenever the product FG makes sense, then that's just evaluation at a point in the closed unit disk. So then using Salas's example, we showed that you can find a multiplier of this space, which is bounded below on the whole closed disk, but such that 1 over m is not a multiplier. So this says that even the one function corona theorem fails on Salas's space. Let me remark that on the Drury-Arvidsson space for finite D, Costea, Sawyer, and Wick show that the corona theorem does hold. So we've seen several examples in the talk of theorems that were first proved in the Drury-Arvidsson space for finite D and turned out to hold on all complete Pick spaces. But the corona theorem doesn't. It holds on the Drury-Arvidsson space, but it won't hold on all spaces. But that's the only function theoretic property of H infinity that I'm aware of that doesn't generalize to complete Pick spaces. Okay, I'll close here. Thank you very much for your attention.
Thanks again to John for a very interesting lecture. There were a few questions. I don't know if we have time before the next lecture starts, but it was asked here, do you know whether the CP spaces of Salas can be embedded in B sub D for finite D?
I don't, but I'd be willing to bet that they can't.
Okay, and then actually this is a question I had from Victor Linnikoff, that any thoughts or comments on the free non-commutative setting?
That seems to be a blossoming area in which in some ways it is easier. We've already seen an example of the Jury-Martin theorem where the non-commutative setting turned out to be easier. And I would guess that in a few years, everything that I said today will have been proved in the non-commutative case as well.